will be on zoomorphic design. The paper is authored by Noah Duncan, Craig Yu, Sai-Kit Yong, and Dimitri Terzopoulos. And Noah will give the talk.
Hi, everybody. Today I'll be talking about our system for zoomorphic design. So first of all, let's talk about what that is. So generally, people tend to be fascinated by nature. That's why we enjoy looking at this image of a horse. But it's not feasible to keep a horse in our homes, so people make horse statues. But from a computer modeling perspective, there's not much difference between a horse and a horse statue. But sometimes we can take an existing type of man-made object like a chair and infuse it with the appearance of an animal to make something like this horse chair. So we call a man-made object that has the form or appearance of an animal like this horse chair zoomorphic. So zoomorphic objects are all around us. Perhaps the most common example is a piggy bank. They've been created for a long time, like this pottery vessel from ancient Iran. And they're also very popular with children. So using our system, it's pretty easy to create zoomorphic scenes. In this example, we created a zoomorphic themed restaurant with a manatee chair, octopus chandelier, some fish dishes, and a dolphin wine glass. And in this scene, we took an ordinary playground and made it zoomorphic. So let's look at some of the unique issues a designer of these objects has to consider. So simply sticking a horse in a chair in the same place doesn't work. We need to take into account certain qualities of a chair, like a flat area for someone to sit on them. And let's consider this horse tricycle. The designer had to make sure that the legs were not touching the wheels, and they had to make sure that the horse's saddle lay in the same place as the tricycle seat. So in these kinds of objects, there's often a trade-off between trying to resemble an animal and trying to be whatever type of man-made object it is. Like this object has the right proportions for an armadillo, but slightly awkward proportions for a chair. And the armadillo's snout might block somebody from crossing their legs. So because of these unique problems, we think computer graphics can contribute to the design of these objects. So our goal was to develop a computational tool which automates the low-level operation necessary to produce these objects while allowing the user control over the high-level design factors. And as a secondary goal, we want our system to suggest novel designs to the user. So there's been a lot of related work in computer graphics on creating plausible, novel, man-made objects by combining existing objects. But in these works, the input objects are all fairly similar to each other. They belong to the same category of object. So our work is unique in that we're combining two objects that belong to very different categories. So we need to come up with a different criterion for making sure that the resulting object is plausible. So our approach takes in two input shapes called the animal shape and the base shape. And the animal shape is the animal that we want to introduce into the zoomorphic shape. And the base shape is a shape from the category of man-made objects that we want our zoomorphic shape to belong to. And our output is a zoomorphic shape, which hopefully retains the appearance of the animal shape and the functionality of the base shape. Our method assumes that these input objects have been pre-segmented into meaningful parts. So first we'll talk about the main technical concepts used in our approach. It's the volumetric design restriction, the deformation models used to change how the shapes are configured, and an energy that measures how good a configuration is. So the volumetric design restriction is our technique for ensuring that the design restrictions of the base shape are preserved in the zoomorphic shape. We can motivate this with a few examples. So say we want to merge the face in the mug into a face mug. If we simply superimpose the shapes, we'll get something that's really not a mug anymore. But we want something with a concave area that can hold water, so it is still a mug. And a less clear-cut example is trying to make a scorpion chair. So again, if we simply stick the two shapes on top of each other, the scorpion's tail is going to block someone from sitting down. But if we slightly alter the pose of the scorpion's tail, we'll get something that's a lot more comfortable to sit down on. So to handle these issues in a general fashion, we're going to partition the volume of space surrounding the base shape into two types of zones, free and restricted. So in the free zones, the geometry from the animal is allowed to exist, while in the restricted zones it isn't. So this partitioning of 3D space can resolve these issues with the face mug and the scorpion chair. So the face mug, just marking the interior of the cup, is restricted, hollows out the face. And for the scorpion chair, the scorpion's tail now knows that it's in a restricted zone, can bend out of that zone. So if we partition space, it seems like a solution, but it's not clear how to partition 3D space. It's not intuitive to do that. And another factor is that our optimization process is going to deform the man-made object. So we want our volumetric partition to adjust itself accordingly. So if we raise the chairs back, we want the zones to change in the same way. So our solution is to define the 3D partition in terms of a labeling of the base-shaped surface. So let's motivate this by showing 4 different cases that arise in this problem. So in the region around the seating area of the chair, we want to preserve a space for someone to sit. We can't have the horse's head go there. So in this case, we want all the space around the seating region to be restricted. So we call this the infinite restricted case. And for the region on the back of the chair, we can add a material wherever we want. So all the space around this region is marked free. So this is the infinite free case. So for the chair legs, a little more complicated, we want to add material to the legs, but we don't want that material to go really far from the legs, like this. So we have a finite buffer of the free zone around the legs, but everything outside that buffer is restricted. So consider this tricycle for the last case. We don't want any part of the animal to touch the wheels, but it can get pretty close to the wheels. So for the tricycle, we have a finite buffer, restricted zone around the wheels. And we do the labeling manually. Just give it to the user to paint the mesh. So we show this process in this video,
which the user provides interactively. Here we show our tool for creating a volumetric design restriction. The user wants to reserve a space on the tricycle seat for someone to sit on. The user paints the tricycle surface with the label that creates this space. Here the user wants to ensure that the animal shape does not contact the tricycle wheels. They create a buffer around the wheels. The size of this buffer can be visualized interactively.
Okay, and another cool thing about doing the labeling is that you don't have to do it entirely manually. If you manually label like a set of meshes, and you can train like a classifier to label a new thing automatically using existing approach and graphics for mesh segmentation. So that works reasonably well. So the deformation models specify how these shapes can actually deform. So for animal shapes, we use 2 different models. For articulated models, we use linear blend skinning. And for non-articulated models like this face, we just use a free-form deformation cage. And for the base shapes, we use a cuboid-based deformation model. We enclose parts of the model in cuboids, and these cuboids specify how the parts are scaled, stretched. So the deformation models specify how the shapes are configured, and you can see there's a lot of ways to configure these two shapes, and many of the possible configurations are bad. So we want to develop an energy that can identify a good configuration for us, then we can minimize the energy. So the configuration energy is a sum of 5 terms. I'll talk about those in a bit. By adjusting the weighting between these terms, we can express a preference for different factors in the final design we produce. So the first term is the animal shape deformation. It just penalizes distortion of the animal. Without this term, we're going to get something really stretched out. With this term, we get something more reasonable. The base shape just does the same thing for the man-made shape. Without this term, the chair is going to have unusable proportions. With it, the proportions are better. The registration term just encourages the two shapes to get close and align with each other. So without this term, you're going to see the horse's legs have drifted from the chair's legs. But with this term, the horse overlaps more with the chair. So the visual salience term, so we say that some parts of the animal shape are visually salient. So we want people to see these parts. So for the face, it's like the eyes, nose, and mouth. And we want visual salient regions to be visible in the final shape. So this term penalizes the occlusion of these parts. So without this term, you see the face is partially embedded in the cup. But with this term, the front of the face is coming out. So the Gash term, so the volumetric design restriction is going to chop off some parts of the horse. And when the animal lies on a boundary between the free and restricted zones, a gash will form where you can see part of the animal shape being removed. So this doesn't look very good. So this term just penalizes the occurrence of these things. So here we can see that the gash term causes the chair's back to raise up and the horse to dip down a little bit to eliminate the gash. So those were the technical components, and I'll talk about the actual method. So the first step, we obtain a correspondence between the segments of the two shapes. And this gives us a rough alignment. The next step, we refine this rough configuration to get something that looks a little better. And then the final merging, we remove some parts from the two shape and then just combine them to get our final output. So in the correspondence search, we conduct a tree-based search across the space of possible partial correspondences between the parts of the two shapes. And each partial correspondence is associated with a configuration, which the two parts are in the same place. And we take the configuration with lowest energy. So hopefully we get something like this. And configuration refinement, we take that rough configuration and make it better with some continuous optimization. So we use a covariance matrix adaptation evolution strategy because the energy is not differentiable. Show that. So after the final configuration is obtained, we get our final output by remove the parts of the animal shape that lie in the restricted zones. So we chop off the back and the tail of the horse. And we remove the parts of the base shape that have been replaced by parts of the animal shape. So you see like the chair's legs are removed because they seem to have been replaced by the animal's legs.
We allow the user to control the trade-off between the base and animal shape deformation in our GUI. Here we show a low base shape deformation. Note how the horse is deformed. If the weight is set lower, the chair will be deformed to match the horse instead. The user can find a good trade-off interactively.
So we also allow the user to kind of interact with our optimizer because some shapes are often enhanced when they're placed in a pose of semantic significance. So like in this case, the user wants the horse to be in a galloping pose. And you can see this position interfered with the rider. So our optimizer is going to fix the user edit. So we'll end up with something that's in a galloping pose, but the head is no longer blocking the rider. So now I'll present some more
This
results.
example shows the creation of an armadillo go-kart. The user can rigidly constrain the armadillo pose. Our approach can create different designs accordingly. We also allow the user to adjust the weighting of terms in the configuration energy. This example shows the creation of a horse chair. By controlling the weight associated with the visual saliency, our approach can create different horse chairs showing different portions of the horse. A rocking horse and a cow merges into a rocking cow. By allowing a larger deformation of the animal shape, our approach creates another rocking cow that is similar to this real-world design shown. Here we show more results. A bear mug, an octopus carousel, a phoenix plane, and a dolphin tricycle. Given a motorcycle and a jaguar, our approach creates a jaguar motorcycle similar to the real-world design. By using several animal objects as input, our approach can create a zoomorphic design with multiple merges, such as the dragon vase shown here.
So I'll talk about some future work now. So this is comparison between our attempt at making a scorpion chair and an artistic design. So we can see the artist disconnected the scorpion's arms in a non-physical manner to move them to the same place as the chair's arms. And our approach can't do this because it would occur an extremely high deformation energy on the scorpion. So instead we place the scorpion arms at the sides of the chair, which might take up a lot of space. And we believe our approach could be extended to handle this case by allowing parts of the animal to disconnect themselves should the deformation energy become too large. And another style of zoomorphic object relies on a combination of texture and geometry, like this chair. And some other zoomorphic objects try to capture the form of animals rather than mimicking their exact surface details, such as this chair in this building. And exploring these alternate styles is an interesting direction for future work. So that's the end of our talk. And we also did a user study. If anybody has any questions about that.
Okay, thank you very much for the nice talk. We have time for questions. Please come up to the microphone, state your name and affiliation, and ask a question. You don't want me to ask all the questions in this session. But I'd be happy to start with one while you're lining up at the mic. So you talked about functionality mostly as a function of space, of like zones that need to be free or not free. But things like the rocking horse or the chair, they have physical properties that need to be retained, like the center of mass should ideally be project between the legs and things like that. So,
Yeah.
So what's your take on this?
Yeah, that's a limitation of our approach, I guess. I guess like a lot of 3D modeling works focus on like plausibility, functional plausibility, rather than like an all-encompassing definition of functionality. So yeah, I guess we're limited to functionality that can be solely discerned by looking at the object, rather than something that would rely on examining the inside of the object.
Okay, and I have another one. I mean, you could, so your approach is to take the two objects and deform them such that they fit, but you could also search for a chair based on the horse you start with, or search for a horse based on the chair that you start with.
Yeah, we actually do that, but we omitted that from the presentation because otherwise we would have gone over time. We think the part of actually synthesizing the object is a little bit more interesting. So yeah, we use a graph kernel-based approach that looks at the structure of the object's parts. And if you look at our paper, you can see the details for that.
Oh, okay, please.
So the question is, why do you focus on animals? Have you considered combining like two different objects from two categories?
Yeah, we did. In our paper, we have an example where we combine a shoe and a chair, like a high-heeled shoe and a chair, to get the shoe's back to sort of bend upwards so that somebody could sit down on it. But in this presentation, we only showed animals. But yeah, there's no intrinsic reason why it has to be an animal.
Thank you.
Oh, okay, if there are no more questions, then let's thank Noah again.